Hello and welcome back. This is the first video of section 15.4. In this section we're talking about the chain rule, and in this video I'll show you one version of the chain rule and motivate where the chain rule is coming from. Now, as we'll see in this section, there's lots of different kinds of chain rules now that we're in functions of several variables. But what I'll show you in this video and in the ensuing videos is rather than just a rule to follow for each individual case, like a separate rule for each case, I'm going to show you a model that works for any case and from which you can derive the chain rule that works in that case. All right, so maybe that doesn't make sense now. Hopefully it'll make sense at the end of this video. Let's get started. So first off, I want to motivate the chain rule. So where might we encounter a chain rule in functions of several variables? Well, let's suppose you're climbing a mountain over time, and your altitude, so let's declare that, let's call that the z variable. Let's say our altitude z depends on, right, where you're standing on the mountain. So maybe say x and y. So we have this altitude function, which is a function of both x and y. So latitude and longitude, you might think, something like that. And then I can recover my altitude at that point. But we're climbing this mountain over time. So what that means is my x and y coordinates, these variables, are changing with respect to a single variable t. So x and y are each functions of a single variable t. So we have x of t, y of t. So now z, our function of two variables, depends on x and y, which each depend on time. So this is the idea of the chain, right? We have variables which are depending on each other in a chain. So we can ask the question, how does the altitude change with respect to time? So what we're after is a derivative of z with respect to t. All right, so these partials, right, we have z as a function of x and y. So we could compute the partial of z with respect to x and partial of z with respect to y. Those will tell us how the altitude changes with respect to our position. But that's not enough in our case. We also want to know, we also need to know how x and y depend on t. So right, what we want is dz dt. The altitude change, rate of change of altitude with respect to this other variable t for time. So notice here, it's not a partial derivative. It's just a regular function of a single variable. Because ultimately, since x and y both depend on time, x of t, y of t, that means z is sort of, we could think of it as a function of time, right? Put in a time value, find your x and y, input those to z, and so ultimately the altitude is just a function of a single variable. So that's what we're after, is dz dt. Okay. So let me show you how we can get a hold of this quantity dz dt. And this is what I'm talking about, the method to use in any case, because there's going to be different relations between your variables. So the idea is to use a tree diagram. Now I want dz dt. I want to know how z changes with respect to time. So I'm going to start with my z. What's changing? And this depends on both x and y. And x and y each depend on t. Now, try not to, we actually do want this to be a tree in graph theoretic terms, which means no loops. So don't use a single variable t down here. We want one for each x and y. And it's just to help us out more. So z with respect to x, I can find the partial z, partial x. And then I can compute dx dt because x is a function of a single variable t. So that's a dx dt, whereas up here I had partial z, partial x, because z was a function of two variables. We can also do partial z, partial y, and dy dt. Putting this all together gives me dz dt. So if I want to go all the way down the chain to t, well, one, I need to find all the chains that go to t. So there's two here, one through x and one through y. And we're going to take products as we move down a chain. So from z to t, we did partial z, partial x, and multiply that by dx dt. Plus, so now there's another chain going down to t, so I'm going to add that to this. This is another way that z can change with respect to time, so it should make sense that we're adding it. And we'll do partial z, partial y, how z depends on y, times how y depends on t. And add those two together, and that gives us how z changes with respect to time. So here is one version of the chain rule in the specific case when z depends on two variables, and each of those depends on a single variable t. So like I said, there's a lot more different things that could go on, right? I could have z depending on maybe three variables, x, y, and z, and maybe each of those depend on two variables, s and t. This is something we'll actually see when we talk about vector fields. We'll see something like this. And in this case, if I want, say, partial z with respect to t, I would find all the chains that end at t. There's three of them. And so that means my chain rule for this situation would have three terms. And in each of those terms, I would have two factors. Partial z, partial x, times partial x, partial t, and then through y and through z. So three terms, each with two factors. So this tree diagram way of finding any chain rule for any situation is it's super powerful. That's my point. All right, that's it for this video. I'll see you next time.